In this video, we're going to be talking about a pressure sensor, and we'll have two different pressure sensors. One will help us measure altitude, and another will help us measure speed. So let's go ahead and get started. So the pressure measurement is done by forming this. We have two solid, so we have a solid region and a solid region. And it's solid, but this is really thin, right? So we have a thin diaphragm. And so this is a zero pressure difference. So it's going straight, right, under zero pressure difference. If there is an external pressure or pressure difference, right, so then it's going to be pushing either down or up on this thin diaphragm. And as it pushes down, it'll basically move, it will provide some tensile stress on those elements, and we measure that tensile stress. And we can say how much it's going to be proportional to that pressure that's being received. So pretty novel. We just have that thin thing and measure how much it's deforming. So again, here's a nice picture showing how small these pressure measurement apparatuses are. That's pretty cool. So we can use it to measure altitude and also velocity. So the altitude measurement, we can formulate a sensor as shown over here. So we're going to have two different chambers. Chamber one is our reference pressure. So it's filled with at a particular pressure value. And then we have a solid wall, and then we have sensed pressure. So in here, this allows flow in and out. So we have this sensed pressure, and if there's lower sensed pressure, then it'll deform out. If there's a high pressure region, if it's higher in pressure, then it'll deform in. And so we'll be able to measure that pressure difference. So from hydrostatics, we can look at depth, and we can say that pressure 2 minus pressure 1 is equal to rho, where rho is going to be our air density, which we are going to assume is constant for the altitudes that the aircraft is going over, and this is below 11,000 meters. Otherwise, that air density causes us issues. G is just going to be our gravitational constant, as always. And then we have this Z2 minus Z1. This is our deviation in our altitude or in our depth. Okay, so if we take that and we take our reference pressure to just be the ground, right? So that's the reference pressure that we want to consider. Then we have the pressure felt is going to be where the aircraft actually is. So we'll get our P times G, or P, that's rho times G, times the height of our aircraft minus the height of the ground. So this is our altitude. So that's what this guy is. Our HAGL is just the above ground altitude. Okay, and so below 11,000 meters, we can use the barometric formula for pressure. So we know what pressure is going to be. And this will take into account change in density with altitude and temperature. So I did say that our air density was constant. Over here, we can actually take that into account. Okay. So if we assume that the density is constant, then we'll just have that our P ground minus P can be modeled as the PGH GL. So that's this formula that we looked at right here, which is really cool. So this is height above ground level. So it's our I keep calling it PG, rho G times H AGL. Shouldn't put a P right above it. But anyway, then we're going to have our bias again. So we typically always have a bias that we have to measure out. And then again, we have our white noise. Okay, so this just shows the validity over different altitudes, right? So for the altitudes that we care about for our aircraft, right, 500 meters for a small UAV, we're doing pretty good. If you take it up to, there's our right around our 1100 meter threshold, then that model ends up not being super great. So again, we have a good. This is a fantastic model for the heights that we really care about. Okay. Now our airspeed, we're going to do slightly differently. So our airspeed, we're going to connect. So if you recall, let's review this one. Our reference pressure in this case, the reference pressure is a sealed container. So we've pumped air into it, and it's not going to be changing. Over here, we're going to have two different chambers, and they'll both be connected to the outside. But our air coming in, so from our V sub A, our relative airspeed coming in, is going to have air pushing into this chamber, which we call the pressure of P sub T. Then we have static pressure, and this pressure has to go around two right angles and up here, right? So the goal here is that we're trying to take away any of the effect of the wind. So all these right angles are eliminating the effect of the wind coming in to push on the diaphragm. So this wind comes in, pushes there. We create just our normal static pressure on this side, and the difference of them is going to help us know how fast our relative airspeed is. So again, from Bernoulli's equation, we can see that the airspeed, the static is equal to, our static plus our rho, got it right that time, times VA squared all over 2 is equal to P sub T. Okay, which is great. Now we can generate a measurement where again we have our bias and our white noise, and then we have the element we're trying to measure. So we can get a fairly decent measurement for our relative wind speed. And there you have it. So we can use these pressure sensors, pretty phenomenal little apparatus to measure both altitude and airspeed.